The method of estimation of simple regression model is given in this section. How we can estimate a simple regression model or a two-variable regression model. Usually, two important methods are usually used for the estimation of regression models. They are ordinary least square estimation method and the second one is maximum likelihood method. In these two methods, the method of OLS is used extensively in regression analysis. The reason is that it has certain mathematical properties and the method of estimation is simple also. The method of ordinary least square is attributed to Carl Friedrich Gauss. He was a German mathematician. It has certain statistical properties and therefore it is considered as a most powerful and popular method of regression analysis. In the following section, we can see the method of estimation of simple regression models using the ordinary least square method. The population regression function of a two-variable model can be written as yi equals beta 1 plus beta 2 xi plus ui. But we know that population regression function is not directly observable. Therefore, we estimate the population regression function from the sample regression function. And the sample regression function can be specified as we have learned in the last class, yi equal to beta 1 cap plus beta 2 cap xi plus ui cap. That is, this cap shows the estimated values, or we can specify it as yi equal to yi cap, where yi cap is beta 1 cap plus beta 2 cap xi plus ui cap. From this, the other term equal to yi minus yi cap. Here, yi cap is the estimated or the conditional mean value of y, and now we want to see how the sample regression function is determined. And from this equation, we derive the other term ui cap equal to yi minus yi cap, where this can be elaborated as ui cap equal to yi is this one minus beta 1 cap plus beta 2. We need a bracket. That is, given an n pair of observations on y and x, we can determine the sample regression function in such a manner that it is as close as possible to the actual yi, or we want to estimate the sample regression function which is as close to the actual or the population regression y or the dependent variable. For this, we may adopt the following criteria, that is, choose the sample regression function in such a way that the sum of residuals is as small as possible. Here, the residuals or the deviation should be as small as possible. That is, choose sample regression function in such a way that the sum of residuals is as small as possible. That is, sigma ui cap must be as minimum as possible. That is, this sum of the difference between the actual and the estimated should be the minimum, or it should be very minimum. This is not a good criterion, and we can see that, or we can prove that this is not a good criterion from this figure if we adopt the criterion of minimizing. The u1 cap, u2 cap, u3 cap, u4 cap and u1 cap, everything gets the same weight. That is, if we add all these terms what we get, or if we take the sum of, as given in this slide, the sum of these terms or the deviations from the sum from the given observations, we will get, or the sum will be sometimes equal to 0. Sometimes it may be very small also. Therefore, we use another method known as least square criterion. Here, the basics of ordinary least square method is that the sum of residual must be as small as possible, but if we take the sum of the residual, sometimes it will be 0 or very small or negligible, then we cannot estimate the population sample regression function. And in order to overcome this, what we usually do is that we use the criterion of least square criterion, or we use a method known as least square criterion. The least square criterion states that sample regression function can be fixed in such a way that take the sum of squares. Earlier we have taken simply the sum only, then sometimes its value will be equal to 0. In order to overcome that, we uses another method known as least square criterion. In that, we take the sum of squares of the array terms. Sum of squares of the array terms, this equation can be rewritten as sigma ui cap square, that will be equal to sigma of yi minus yi cap the whole square, or sigma ui cap equal to yi minus yi cap can be substituted as beta 1 cap plus beta 2 cap xi the whole square. That is, ui cap square is a function of beta 1 cap and beta 2 cap. The sum of squares of this array term must be as small as possible. When we use a squaring, when we take the square, we are giving more weights to the residuals which are far away than the residuals which are nearer. We will more weights will be given to this one, means even if it is negative or positive, if we square it, we will get a positive number. Therefore, these terms will get more weights than these two weights. That is the logic behind the least square criterion of taking sum of squares of the array terms. Therefore, the principle or the method of least square chooses beta 1 cap and beta 2 cap. Here, array term is a function of beta 1 cap and beta 2 cap, and the principle or the method of least square chooses beta 1 cap and beta 2 cap in such a manner that sigma ui cap square is as small as possible. Or, in other words, for a given sample, the method of least square provides us with unique estimates of beta 1 and beta 2, which will give the smallest value for ui cap square. And how it can be possible is explained in the following section. Here, we are going to explain the method of least square. The method of least square states that the sum of squares of residuals must be as small as possible. If we take the sum of squares, if we take the sum of these residuals, sometimes it may be 0 or very negligible. In order to avoid that problems, or in order to give more weights to certain array terms, we uses another method or the principle known as least square criterion, and on the basis of least square criterion we can estimate the beta 1 cap and beta 2 cap. From this, least square methods will provide a unique estimates of beta 1 and beta 2 cap, and it will give the smallest possible value of sigma ui caps. That is, the error must be minimum. That is, error means the deviations from the actual are the estimated. If the deviation is higher, then it is not equivalent or it is not nearer to the population regression function. If the estimated value is nearer to the actual value, then if the estimated value is nearer to the actual value, then the error term will be as small as, or in order to make the sample regression function closer to the population regression function, the error term must be very minimum. In this section, we are going to estimate the beta 1 and beta 2, and the method used for estimating the beta 1 cap and beta 2 cap are known as the method of least square. And we have, in order to estimate the beta 1 cap and beta 2 cap, or to estimate beta 1 and beta 2, which is a function of, we have selected the least square criterion method, and least square, according to the least square criterion method, is that we are taking the sum of squares, and sigma ui cap square equal to yi minus beta 1 cap plus beta 2 cap xi square. This is the least square criterion, or sigma ui cap square. From this we can derive the beta 1 and beta 2. Ui cap square equal to sigma of yi minus beta 1 cap minus beta 2 cap xi square. We have removed the bracket, and therefore it will be yi minus beta 1 cap minus beta 2 cap the whole square. Then now we are going to estimate beta 1 and beta 2, or we want to estimate the numerical values for beta 1 and beta 2. For that, take the partial differential of this function with respect to beta 1 and beta 2. Here, this is a function, and we have two parameters to be estimated, or to be for the estimation, and take the partial differentials of this function with respect to beta 1 and beta 2. Therefore, the partial differential is given as, partial differential is denoted as this partial dou, or the dou sigma ui cap square divided by dou beta 1. That is, this in the first case we are deriving the partial differential of this function with respect to beta 1. Then we will get the differential of this function is, that is, if we treat this as u square, then 2 into u, that is yi minus beta 1 cap minus beta 2 cap, then the differential of beta 1 cap, that is this minus 1 minus, then the differential of beta 1 cap is minus 1. Therefore, we will get the differential of this function, that is sigma ui cap square equal to sigma of yi minus beta 1 cap minus beta 2 cap xi the whole square, as 2 into sigma of yi minus beta 1 cap minus beta 2 cap xi minus 1. Then this can be written as, this minus 1 can be multiplied by this 2, then we will get minus 2 sigma yi minus beta 1 cap minus beta 2 cap xi, or this can be written as, this sigma yi minus beta 1 cap minus beta 2 cap xi is nothing but ui cap, that we have seen in the last slide. That is, this term is nothing but the ui, and therefore this equation can be written as minus 2 into ui cap. Similarly, we can obtain the partial differential of this function with respect to beta 2 cap, that is dou ui cap squared divided by dou beta 2 cap equal to the same way 2 into sigma of yi minus beta 1 cap minus beta 2 xi, and here a differential of beta 2 cap is, here we have xi also, differential of beta 2 cap is minus 1 into xi, that is minus xi. In the same way, we can multiply this minus 1 with this 2, then we will get minus 2 sigma of this function itself and the remaining portion xi. Therefore, and this can be written as, here this yi minus beta 1 cap minus beta 2 cap xi is nothing but the ui cap, and this function can be rewritten as minus 2 sigma ui cap, and the xi, that is minus 2 sigma ui cap minus into xi, minus 2 sigma ui cap xi. This is the second equation. The first equation is this one, and the second equation or the second partial differential of this function with respect to the beta 2 cap is this one. In the next step, we are going to set these two equations equal to 0. That is simply equate these to 0. That is minus 2 sigma yi minus beta 1 cap minus beta 2 cap xi equal to 0, or minus 2 sigma ui cap equal to 0. Similarly, equate this also equal to 0. Minus 2 sigma yi minus beta 1 cap minus beta 2 cap xi into xi equal to 0. That is, or minus 2 sigma ui cap into xi equal to 0. The first step what we have done is take the partial differential of this function with respect to beta 1 and beta 2. Second step is equate the differential equations of beta 1 and beta 2 equal to 0. This is the second step. In this equation we can see that minus 2 into sigma ui cap equal to 0 and minus 2 into sigma ui cap xi equal to 0. From this, minus 2 can never be 0. Only this component can be 0. Here also this minus 2 can never be 0. Only this term can be 0. Therefore, sigma ui cap, it is assumed, or it is considered that sigma ui cap equal to 0 and sigma ui cap xi equal to 0, since minus 2 can never be equal to 0. Then if minus 2 is removed, or since it is not equal to 0, we consider this yi, sigma of yi minus beta 1 cap minus beta 2 cap xi equal to 0. Similarly, sigma of yi minus beta 1 cap minus beta 2 cap xi into xi equal to 0. Now we are going to distribute this sigma throughout the equation. And if we distribute this sigma throughout the equation, what we will get is sigma yi minus, now we are going to distribute the sigma and remove the bracket. That is, we are going to do sigma yi minus sigma beta 1 is a constant, then sigma beta 1 can be written as, suppose we want to get the sum of x plus x plus x, then we will say 3x. Like that, here x plus x plus x is number, 3x is 3 number, the number is 3 into x. Similarly, we can take the sum of beta 1 cap equal to n. n into beta 1 is the sum of this constant. Then beta 2, here we have a variable, therefore we can give that, take the sum of that variable, that is sigma x. And similarly, distribute sigma to the second equation also, sigma yi n beta 1 cap. Here it is not n beta 1 cap. We before that multiply this equation with xi. Then we will get sigma yi xi minus beta 1 cap xi minus beta 2 cap xi the whole square. Then distribute the sigma. Here we will get sigma yi xi beta 1 cap sigma xi beta 2 cap sigma xi square. In the next, here what we have done is that we distributed the sigma. The only thing here, the sigma, instead of putting sigma, it is better to keep, or it is correct to put n, since it is a constant. In the second case, we have a variable and we are multiplying it with that, then we can distribute sigma with that variable. And after that, we can derive two equations from this equations, 5 and 6. The equations are sigma yi equal to n beta 1 cap plus beta 2 cap sigma xi, and sigma yi is xi equal to beta 1 cap sigma xi plus beta 2 cap sigma xi square. That is, from the above equations, we can, from the equation 5 and 6, we can derive two equations. On the one hand side, y, the dependent variable, and the other hand side, the other parameters and the variables, or the independent variables. That is sigma yi equal to n beta 1 cap plus beta 2. This is derived from this equation, and this one from this after distributing the sigma and multiplying with the xi. Now, these equations can be solved. We can solve these two equations. After solving these two equations, we will get, or we can derive the parameters of beta 1 cap and beta 2 cap. From solving these two equations, we can derive the value of beta 1 as well as beta 2 cap. And the value of beta 2 cap and beta 1 cap derived from this equation can be written as n into sigma xi yi minus sigma xi into sigma yi divided by n into sigma xi square minus sigma xi the whole square. This is in capital form. X and y, all x and y are in capital letters, and this can be written like this also, that is beta 2 cap equal to x minus x bar, xi minus x bar into yi minus pi bar divided by xi minus x bar the whole square. And here in this also, this xi minus x bar and yi minus y bar, xi and yi are capital letters, that is xi minus x bar into y, that the deviations from original actual, their mean value y bar and x bar are mean values of the dependent and independent variables. And this can be written as xi minus x bar can be denoted as small xi and yi minus y bar as small yi. Here x in the denominator we have xi minus x bar the whole square, and it can be written as small xi. Therefore, this equation can be written as sigma of small xi yi divided by small xi square. Equation can also be derived as sigma xi yi divided by sigma xi square minus x bar. Here this xi is small letter and yi is capital letter. This xi is capital letter. And similarly, we can use capital letters also in this case, sigma xi yi divided by sigma xi square minus nx bar. That is, if we take the capital letters of x and y and divide it by sigma xi square minus nx bar, also we can, if we take the capital letter of xi, then this should be small letter, and if we are taking this as capital letter, this should be in deviation form. In this way also we can derive the value of beta 2 cap. And if we beta 1 cap can be estimated as sigma xi square into sigma yi square yi minus sigma xi into sigma xi yi divided by n sigma xi square minus sigma xi the whole square. Here also all the letters are capital letters. That is sigma xi square into sigma yi minus sigma x into sigma xi yi divided by n sigma xi square minus sigma xi the whole square. All these derivations are obtained from the above two normal equations. Or beta 1 can be estimated as follows also, that is y bar minus beta 2 cap x bar. If we have beta 2 cap, we can directly obtain beta 1 cap. The formula is y bar, that is obtain the mean value of the dependent variable and take the difference of beta 2 cap into x bar. Then we will get the beta 1 cap, or beta 1 cap equal to y bar minus beta 2 cap x bar. Estimators obtained in this way are known as least square estimators, since they are derived from the least square principle, or for estimation we have used the least square principle. Least square is take the sum of squares of the array term. From that we can derive the beta 1 and beta 2, or beta 1 cap and beta 2 cap as follows. Here the first step is take the least square equation. Second step is take the partial derivatives with respect to two parameters beta 1 and beta 2. Third one is equate it equal to 0. Then distribute sigma. Then take the two equations. By solving these two normal equations, we can find out the value of beta 2 cap and beta 1 cap. We can derive the value of beta 1 cap and beta 2 cap in different combination. Here capital Xi and small xi simply means we can estimate the value either by using the actual observation or taking the deviations from the mean value. That is why this small value and capital value arises in this equation. In both way we can derive the equations of or derive the numerical values of beta 2 cap and beta 1 cap. These are the various formula that we can use for estimating the simple beta 2 cap. And for estimating beta 2 cap we have 1, 2, 3, 5 different equations or different values, and beta 1 can be estimated using these two.